All right, this is the video for physics for Monday, and a couple of things about the playlist for today. So first off, we're going to talk in this video about the Finnish Fling here in a moment, which also ties into the Wall of Death on how that works. And then you're going to watch a physics girl video about one of the at-home experiments that you can try with the basketball and the golf ball, or the two bouncy balls. And then there's going to be a rope coil effect video. And I want to let you know the rope coil effect video, that's to begin to explain what some of you tried with the rope coil effect. That's not something we'll ever have any type of assessment, or I'll ask you to explain or anything like that. The bouncy ball stuff will start to make a heck of a lot more sense as we start our next topic, which will be later this week. There will also be a how to go to space today video. We watched this a long time ago, but now that you know a heck of a lot more about gravity and orbits and motion, I think it'll make a lot more sense. It might still be a little bit entertaining as well. And then there will be an OK Go video, another OK Go music video. These are the guys that did the parabolic flight where they were singing and stuff, where they really went out and did it. Multiple takes, but they went out and did it. They have a good video with explosions. So later this week, we're finally going to start to deal with when something hits the ground, or when you're throwing something, when like Mario Ball's in your hand, or when something explodes. Because when we talk about throwing or catching, that's or something hitting something or something exploding, those all have to do with the same ideas, where we're going to apply some ideas that have to do with momentum. Okay, but that's not quite today yet. The OK Go video is just like a look ahead, look at this neat thing. And when you're watching that video, just notice some of the symmetry to the explosions. Like there might be a big chunk goes to the left, and there'll be a big chunk that goes to the right. Like the symmetry, the prettiness of the stuff that they blow up in that video. Okay. All right, so let's go ahead now. That was just a quick little look at the week and the playlist that you're going to be watching today. Now let's go ahead and get our Finnish Fling explanation. So now, as somebody mentioned in one of their emails that they didn't think the ride was there anymore at Worlds of Fun, I think you're correct. It has been removed. But those rides still do exist. And there are variations on it in lots of amusement parks where you stick to the wall and the floor drops down. And I should also mention here in OneNote, my OneNote, whenever I do something where I write on OneNote, you still have access to it just like always. Physics second semester, if you're looking for my notes, okay, on this. You're also welcome to pause the video and take notes at home if you're a note taker. That's a great idea, okay? All right, so let's go ahead and talk about the Finnish Fling. And I'm going to go ahead and draw a person stuck to the wall, okay? So there's my person, and they're stuck to the wall, and the ground is down here. The ground is down here, okay? Now, normally, when there's a person stuck to the wall, normally, if we would draw that picture, we would expect the object to slide down the wall, right? You wouldn't expect the person to stay there. But obviously, you saw the video where that doesn't happen. So the question is how? How could that be happening? So I'm going to go ahead and draw a free body diagram here, the starter free body diagram. We know we have force of weight or force of gravity going down. So we know we've got some force of gravity going down. So there must be, if we're going to not move down at all, there must be a force upward. The question is, what is that force? So take a minute and pause and see if you can think about what would keep us from, here's a big hint, from sliding down the wall. All right, welcome back. Hopefully you took a guess and thought about what it could be. It actually is friction, okay? And if we're not sliding down the wall, it'll be force of friction static. Force of friction static. So we got static friction keeping us from sliding down the wall. So static friction up, force of weight going down. Now that can't be it, because under normal circumstances, there wouldn't be enough static friction to keep you stuck to a wall. So the question then becomes, why is that force of friction static at least equal to your weight? So we're asking, like, why is this so darn big for this problem, okay? And it's not, let's write the equation for static friction. It's not because of the coefficient of static friction, okay? Your coefficient of static friction between your clothes and the wall, I mean, don't try this, but if you went and threw yourself at the wall, you would just slide right down, right? Okay, so the room spinning has to do with this. So now I gotta make you understand that the center of the room is right here. So this thing is spinning around, the room is spinning around, the floor has dropped, and the center of the room is right here. So if we're gonna go around in a circle like this, At that moment in time, when I say the person's right here, okay, on my picture, there must be some force in towards the center of the circle. So we've got to have a force going this way. Otherwise, at that moment in time, that person would just fly off at a tangent line, like when I let go of, or talked about letting go of that little brain on the string in one of my videos, okay? So there's got to be some force pushing it inward. Well, if you remember I think it was a washing machine question. Okay, if you think about a top-loading washing machine, why are all the clothes stuck to the sides of the, what's the force that makes the clothes go around in the washing machine? So if you think about a top-loading washing machine, where you put the clothes in, it spins, and you notice that all the clothes get stuck to the side of the walls. Okay, similar idea to the Finnish Fling. What's the force inward there that allows them to go around the turn? It's the walls. Same thing here. The wall is in contact with you and exerts a force. So now we're back to a contact force that is perpendicular to the wall. So if this is our wall, okay, that would be the direction of our perpendicular contact force. We have another name for that. It's called the normal force. So our normal force on this problem is the force that's making us go around in the circle, and it points that way. From that perspective, that picture there, freezing it at that moment in time. Whoops. Okay. So our normal force is the force that is inward towards the center of the circle. Okay. This is also similar to that, the skaters that were going around the loop-de-loops. Okay, there was always a normal force pointed in towards the center of the circle. That contact force is what's allowing us to make the turn. The wall gets in the way is another way to say it. The wall pushes you in. The wall gets in the way. That push of the wall, the normal force. Now, if I sum my forces along the radius, equal to mass times centripetal acceleration, I've got that normal force equals mv squared over r. So this goes back to our problems that we did where there's like one force over here. In this case, it's the normal force equals the mass of the person times their speed squared over r. So as the room spins faster and faster, this increases how fast the object's spinning, which means the normal force has to get bigger. This assumes the wall doesn't break, okay? So the normal force has to get bigger and bigger and bigger, okay? And you can feel this, okay, when you're on this, or if you've ever been on one of these rides, okay? That normal force gets bigger and bigger and bigger. So if that normal force is getting bigger and bigger and bigger, okay, and this is staying the same, our force of friction static max gets bigger and bigger and bigger. Until at some point, force of friction static max will be bigger than our weight. So we have plenty of static friction and you don't slide down, okay? In reality, at that point where you're stuck, static friction would equal the weight, but the maximum value would be more. Now, occasionally, if you've ever been on one of these rides, you might see somebody slide down. It is not, as long as I'm going to make it simple. We're going to assume that if they're a larger person, their belly is not way out to here. So as long as they don't have a gut way out to here, what I'm about to say is true, okay? The mass of the person doesn't matter, okay? So it has to do with the coefficient of friction between their clothes and the wall that they're on. So that could be an issue with what they're wearing, how that wall, the carpet on the wall there, how it's worn over the years. It could be if they're sweaty. It all has to do with mu sub s, okay? That's what's going to allow someone to slide down the wall and somebody else not to. So the mass doesn't matter, okay? The mass of the person doesn't matter. It cancels out if you actually work through the algebra. The thing that matters is the coefficient of friction, okay? Assuming, again, we don't have to worry about any rotational effects, okay? All right, so now what about the wall of death thing that you saw, okay? Very similar idea. Or for motorcycles and for cars. You get going really, really fast in a circle. Instead of the room spinning, the car goes around, okay? And instead of that person, picture that as a car, okay, or a motorcycle. There'll be a big normal force inward, and at some point, as that car goes faster and faster and faster around a certain turn, the normal force will go up. As the normal force goes up, the force of friction static max goes up, and then there's enough to support even the weight of a car, okay, so that the car doesn't slide down. Now, when we watch that, or when you watch that wall of death video, you'll notice, and you can go back and watch it again, but as the motorcycles and the cars slow down, they have to go back down. Otherwise, they would start to slide and then probably roll down the hill. So once they start to slow down, they do need to drive back down to the bottom of the wall there. Okay, so that was some explanation there on Finnish Fling and wall of death. Again, it's about the room. Quick little review here. It's about the room spinning fast. The room spinning fast to increase the normal force. As the normal force goes up, maximum static friction goes up, and eventually you get enough of this to support the weight of a human being. And then you're stuck to the wall, and it's fun. Just mention again about the playlist. Make sure that for the at-home experiment that you try one of those and submit pictures or videos. You don't have to explain it. You're going to get a video explanation of one of them and learn more about it going forward. Okay, that's it.
There's still a car explosion over there.